a special warm-up for you today. Give these a try. We'll be doing some logarithms today, and so after this warm-up, we'll jump right into a review of some basic, or rather important, logarithm facts. So pause that video, give these a try. Okay, hopefully you gave them a try. Let's go through this real quick. I'll give myself a bit of room here to do this. Looks like it's an implicit differentiation problem. The way this equation is written is implicitly, because those y's aren't isolated. When we isolate the y's, we call it explicit. So let's implicitly differentiate this implicitly defined equation here. So derivative of y is dy dx. Some people will write y prime. I do recommend that you use the Leibniz notation here. Quotient rule says leave that cosine alone. Next, we're going to, not quotient rule, sorry, product rule. Product rule says leave that alone. Plus, I leave the y alone. Derivative of cosine is negative sine. Those parentheses are definitely our friends. Okay, so we did the left side. Let's do the right side. Again, it's a product rule, so the derivative of x is a 1. I leave that sine of y alone, nothing to do with that. Times, I need the derivative of sine is going to be cosine of y. But I'm not done, because y is a function of x, at least we're treating it as one, and so we need to multiply by the derivative of y is dy dx. Okay, so pretty good. We just need to find dy dx at those points. There's two ways to do this. One is to solve for dy dx right away. The easier way is actually to plug in pi over 2 right now. Let me do this the hard way, and then I'll do it the easy way. So the hard way is to solve for dy dx, which you should know how to do. We're going to bring everything with the dy dx to one side. So that would be my cosine of x. And it looks like I also have a minus sine of y cosine of x. When I bring those over, I'm doing this a little faster now. I know I'm bringing them over to factor out that dy dx. So if you want to bring over both of those terms separately and then factor them out, but that's why I brought them over, so I can do this in one line. And I give you permission to do it in one line also. Everything without a dy dx looks like it's just going to be that negative y sine x. So I bring it over, it becomes a positive y sine of x. Great. Why did I do this? So that I could divide everything by that left side to isolate that dy dx. Dy dx is equal to y sine of x over everything on that left there. Whew, it's kind of big, but we can do it. Cosine of x minus sine of y cosine of x. Boom. Yeah, it's a little big, but it's not that bad. It didn't take that long. So we still need to plug in that pi over 2 to get an actual number out. Okay, so we could do that there, and we get a number, but we also could have, maybe should have, done it right from the get-go to make our simplifying easier. Why not plug in those numbers the second you take the second after you take those derivatives? So cosine of pi over 2, do you know it? It's just a 0, plus y, well, we're saying it's at when y is pi over 2, times negative sine of x is, well, if x is pi over 2, that becomes a negative 1. Cool. Equals, we've got that 1, sine of pi over 2 is again a 1, times cosine of pi over 2, that's a 0. Very cool. So this is going to be 0 times, well, dy dx. But that's going to go away. Solving this all out, looks like it just becomes dy dx equals pi over 2. Easy peasy. Quite a bit easier, I think. Less writing. So if you know the numbers you're going to plug in, and we'll see this again in related rates, just plug them in after you take the derivative. It'll make your life much simpler. This should be exactly what we get if we were to plug in up here as well. In fact, it is exactly what you get. let's move on to some of this logarithm stuff, as well as a log review. So, natural log of e to the x, as well as these other natural logs. They're all meant to remind you of some log rules. So let's go full steam ahead into this review. We're going to do a couple of quick examples here, and then remind you of these rules a little bit more formally. But really, if you realize that you don't know something and you really don't know it, you might need to go back and practice or remind yourself. So natural log of e to the x, those are inverses. They should undo each other. This really is just x. Okay, natural log of x times y, that's our old friend natural log of x plus natural log of y. Multiplying on the inside is the same as adding on the outside. Adding on the inside, you are stuck adding on the inside. You really can't do anything. Okay, that is a really common mistake, and if you write this as natural log of x plus natural log of y, you've probably destroyed your problem. And it's probably pretty hard for you to do any of the work you were supposed to do because your problem is now so much easier. Okay, back to the left. Natural log of 2, the log base 2 of 2 to the x, those are inverses of each other. Just like natural log an e to the x, that's how we define them. This should be an x. Natural log of 2 to the x, well, the x, this is our amazing exponent rule that x can come down in front. Natural log of 2. And again, e to the natural log of x, those are also inverses of each other. This is just x. Okay, so if you knew those are really fast. If you didn't, your head is spinning right now. Oh my gosh, that is so much stuff that I do or don't remember. So let's real quickly talk about the whys and the wherefores for these things. The first thing I want you to remember is that this is what an exponential looks like. It doesn't matter if it's e to the x or 2 to the x or 10 to the x, some b to the x. It's always positive, and it grows really, really fast, and it should go through the point 0, 1, because if I plug in a 0, I'll get a 1. Our logarithm, log base b, is the inverse of that. And if you graph an inverse, you reflect it over the line y equals x. Why? Because all an inverse does is it switches your x's and your y's. Right? One function takes an x to a y, that inverse takes the y's back to the x's. So if I flip all my x's and y's, then my domain, all real numbers here, that domain should become my range. I get to all real numbers, and my range, just the positives, becomes my domain. So all my logs are only defined for positive numbers. They have this vertical asymptote here, where b to the x has a horizontal asymptote. This grows really fast, this grows really slow. This goes through 0, 1, this goes through 1, 0. And this log base b is asking us b to the what is x. So b to the what is 1, while b to the 0 is 1. All right. What does it mean to be an inverse? It means a couple of things, but one of the things that might be useful right away is that they undo each other when you compose them. So 2 to the stuff with an inner function of log base 2 of x, 2 to the stuff, is just going to be, 2 to the log base 2 of x. If those are inverses, they should undo each other. Out pops x. Just like log base 2 of 2 to the x is also x. This one, it might be a little easier to see if you know your exponent rule. So my exponent rule says this x comes out front if there's an exponent on the inside. So I could write this as x, let's do it in green, x log base 2 of 2. X log base 2 of 2. Okay, so log base 2 of 2 is 1. Natural log of e is 1. Log base 10 of 10 is 1. 2 to the what equals 2? 1. So this is just x. Okay? And again, what is this saying? Log base b of x is saying b to the what equals x. Okay, hopefully this is just a review. It's ringing some bells to remind you. If this is the first time you've really looked at logarithms, then this is going to be way too fast. All right, So let's look at a few of these things. Log base b of b. I just said out loud, b to the what is b? It's a 1. Just like natural log of e. Natural log is secretly a log base e. So e to the what is e? That's a 1. If I don't write a base, it's called the common log. That is really going to be log base 10. There's a little secret 10. Just like there's a little secret e here. So that's going to be a 1. Okay. So whenever you plug that base back into it, you should get a 1 out. Because e to the 1 is e. 10 to the 1 is 10. All right, you may recall that we had a few log rules. We've already used some. So let's write them down more formally. Our log rules that you should have seen and hopefully at some point had explained why they're true. Worst things that you could do than justify these and convince yourself that they are true. But any log, doesn't really matter. Multiplying on the inside becomes adding on the outside. And this will be really helpful for us. Dividing on the inside is subtraction on the outside. Okay. And having an exponent on the inside, that exponent, this is also really important, can come out front as a multiplier. Okay. So what logs do for us pretty magically is they take more complicated operations and they turn them into simpler operations. And this is incredibly useful. This is actually where they're first used, was in multiplying really big numbers and turning it into addition. So we like logs for that reason. This is enough. I'm going to leave the change of base formula off for a second. Let's see if we can solve this equation. You can do whatever log you want. I'm going to tend to use natural logs no matter what. But log base 2 in this case would be a good idea to solve this. If there are x's in an exponent, chances are you're going to need to use a log to bring them down. So I'm going to take the natural log of both sides. Algebra tells me if I do it to both sides, it's fair. My log rule says I can bring that x plus 1 out front. My log rule says I can split this up into natural log of 5 plus that x can come down, natural log of 3. Great. So I successfully got all those x's out of the exponents. Let's bring everything with an x to one side. Okay, to bring everything to one side, we should maybe expand this left side out first. X times natural log of 2 plus natural log of 2. All right. Now I can bring all the x's to one side, so I get an x times natural log of 2. When I bring over that natural log of 3, I get minus natural log of 3 with those parentheses. Going a little fast here. Looks like on the right side I get a natural log of 5. And then I'm going to get a minus that natural log of 2 that didn't have an x on it when I bring it over. Okay, so treating you as a little bit more mature mathematicians who maybe can skip a step here or there. But if that confuses you, see if you can do it on your own before watching me do those steps. So almost there. X equals natural log of 5 minus natural log of 2 all over, dividing that left side, natural log of 2 minus natural log of 3. Okay, this is a little bit weird because it's possible if you use a different logarithm or you took slightly different steps that your answer looks a bit different, despite being the same. Because we have these log rules, we could rewrite those minuses into a single log. We might also use a different base instead of natural log. So for instance, to reconcile this, we would need our change of base formula. If I want to change a base, say into a natural log, what I have to do is just do a natural log of x over that natural log of b. Or into some other base, natural log, log base c of x over log base c of b. We have this really nice change of base formula, so sometimes one person will just have more logs in it, written as a quotient, because they wrote it in a less easy base. So, for instance, let's just take this natural log of 5 over there. If I wanted to write this as log base 2, this would be log base 2 of 5 over log base 2 of e, because e is the base of that other function. Whew, what a whirlwind. Hopefully that's enough to remind you, enough so that you can follow along. But take a second, review all those things, make sure they sit in your head in a nice place so that you're not, at the very least, you're not fighting with them, and you know when to think to yourself, I bet I shouldn't be doing this, or I bet there's a different rule that would make this easier. All right, that was a longer one. Thanks for playing along.